pleased to introduce the speaker for this session, Peter Blaser. Peter is Vice President of Operations at CPFD Software with over 20 years experience developing and applying specialized computational fluid dynamics technologies. Peter is passionate about removing the guesswork surrounding the design and operations of fluid particle processes through intelligent use of digitalization technology. Peter holds a Master's of Applied Science degree from the University of Toronto. It will now be our pleasure to hear from Peter Blaser.
Well, hello everyone and welcome. We're going to talk about powering the impossible, addressing some of our planet's toughest sustainability challenges and how specifically simulation software, GPU computing, and cloud infrastructure come together to make the impossible possible. Thank you for joining me. Before we launch into the details of it all, I'm going to show you some photos. I'm going to ask you a question about what you see in these photos. I like to spend time outside. So here's some outdoor photographs. Here's the first one. Not quite pretty. What do you see? It's a trash dump. Yes, I took a photo. We are showing a photo of a garbage dump. All right, let's go to a different one. Let's go with something a little prettier. Let's go to the beach. And here's a beach covered in plastic waste. And when you see these, let me ask you a question. Do you see problems? I hope so. I certainly do. Do you see impossible challenges that our planet's facing? But do you also see possibilities? And really that's what we're going to be talking about today. In fact, we're going to look at 3 enablers that are powering the impossible, how simulation software, GPU computing, and cloud infrastructure come together to enable and really accelerate how we address some of our planet's toughest sustainability challenges. So let's get started. In fact, we'll start with simulation software. So I'm with CPFD Software. We have a product called Barracuda Virtual Reactor. Virtual Reactor models the 3D transient hydrodynamics as the multi-phase fluid particle flow, thermodynamics, and chemical reactions in industrial units. It is used to improve the reliability and the performance of large industrial systems. It's a mouthful. Basically, it lets people, for operating units, look inside and see, what could be going wrong? What's the root cause? Performing testing virtually on the computer, optimizing systems. And where we're going to land the plane today is on, for those developing new technology, it lets them broaden their R&D and then accelerate that commercialization and scale up, specifically for sustainability technologies. So let's look at traditional use first. This first use case is for refinery risk reduction. And just to let you know what to expect today, I am not going to get into a deep technical dive on any of these. There's at the bottom of the slides footnotes. You can find publications, you can find webinars, video presentations, talks by people. That's where you get the technical details. I want to pull this to a 30,000 foot level, no pun intended with the aerial view of the refinery, and look at the big picture and what does it mean. So this case came from the Viva Energy's Geelong refinery in Australia. And this refinery is multiple components. You see tanks, there's industrial units. There's something called a fluidized catalytic cracking unit, or FCCU. And what was happening is the FCCU got a little hot in places. As a result, the operators needed to intervene and pull back for certain feeds that came in, certain crudes, pull back throughput to the point where it was actually costing them tens of thousands of dollars per day. Now, good news and bad news. Good news is you can make changes to the FCCU. This is called the turnaround. It's when they shut things down, they go in, make changes. The bad news is they come about every 5 years or so, and so you better get it right. So the FCCU here, if I zoom in, this is called the regenerator on the left. Simulation software was used, virtual reactor in this case, to look inside, look at how things are moving. The root cause of the hot temperatures was identified on the far right in the green color. You're going to see the carbon monoxide. It's going to be formed, should be gone before it leaves the unit. It's not. The engineers could start looking at the asymmetry, start exploring what caused that. virtual testing of changes, and they implemented those changes at a turnaround in 2016. They then compared results from 12 months of operational data before and after the turnaround, and were able to operate at lower temperatures. The operator intervention went down 75%, and they could run a 4% higher throughput. Significant difference. So this is a typical use case for virtual reactor. That's refining, used a lot in the cement industry, with increasing use for decarbonizing the cement industry. Again, this is a case presented by one of our European clients. In Europe, the big driver has been decarbonization. So what most people don't realize, cement production probably accounts for something like 8% of the world's CO2 production. This is a big number. It's typically used produced by burning coal, and there's a big driver to renewably source the fuel needed to produce the cement. Inside it is something called a calciner. Here is part of the preheater system, where the coal and the clinker go in, move through the system. Again, I'm not getting the technical details, but as you move toward alternative fuels other than fossil resources, the way in which it moves through the system, the way in which it combusts is different, and changes are required. Virtual testing of those changes is a great way to do things right the first time. Here is a case presented at our 2022, this year's users conference, where they were trying to address two things. One was reduce emissions. So here is several years worth of monthly average CO emission data before a turnaround. They proposed some changes, tested it, implemented it, and they took the baseline CO, sort of what would happen on average. After the change, they were able to reduce the CO emissions between 70 and 80%, depending what month you're looking at. But in addition, this was at the same time done while increasing the thermal substitution rate by 22%, replacing fossil resources in the fuel with sustainable resources. Sometimes sustainability applications are costly. This paid for itself in 6 months. So this is how the software is traditionally used. But let's start talking about some of these crazy uses, some of these impossible uses. So let's start by imagining the impossible. Go back to my first pretty picture of the garbage dump. A company called Thermochem Recovery International, TRI, started asking the question, what if the carbon in the trash could be recovered? And not just recovered, right? So it's not sitting in a landfill, but put to use. Fast forward to this year, another company, Fulcrum Bioenergy, and their project Sierra, started up, and here's a picture from when they were building the unit, a 500 ton per day trash to net zero carbon fuels plant, producing sustainable aviation fuels right here in the US in Nevada. Fantastic reimagining of what's a problem into a possibility. How'd they get there? Part of it, in the middle of it, TRI designed something called a gasifier. Gasifier takes solids, makes it into gases, into chemicals that can be used. The traditional way to build and scale up is to have a concept, and then there's the testing of it, and it's at the lab scale and at the pilot scale and a process demonstration scale and at full scale. And TRI was using simulation software throughout. Barracuda was used at all scales to de-risk this project, to bring it to reality. Their presentation in 2019 at our users conference included this chart. I won't go through all the details, but it looked at how when they started till 2019, how much faster the software got. And you'll see in the end, it was 68 times faster, the bar on the right, than at the beginning. But look at the years that this took. This is between 2009 and 2019. Now, we were ecstatic, still are at that point, that was amazing. But it highlighted the need for speed, how important it is to get calculations through quickly. So that's simulation software. Let's move to the next concept here, the next enabler, GPU computing. And GPU, these are graphical process units, originally graphics cards. A company called NVIDIA started making them programmable in the 90s. Early adopters in the 2010s were 2000s were starting to do scientific computing on them. And here we have an image of an NVIDIA A100 GPU. We parallelized our software on NVIDIA GPUs. 2014 was the release. And here's what's really important about these. There are a lot of cores on a graphics card. So the GPU has, this A100 has about 8,000 cores versus around 100 maybe in some of the most powerful CPUs. Many have less than that. Plus you can put multiple GPUs in the system. So on the right I'm showing a DGX A100 system. This has 8 of those GPUs in it, so about 64,000 cores in a single box. And why does this matter? So not only do you get more cores, but CPU performance has been not accelerating as fast as it used to. So for years, I remember as a kid, every year and a half, so the computer speed would double. This would happen consistently. It happened for a long time. It was known as Moore's Law or Denard scaling. And predictably, they'd be getting faster. And something happened there. So if you look at the plot on the lower left, the blue line, right around 2010, this trend slowed down a lot. And as you can no longer get these transistors closer and closer to each other on the chip because of thermal limitations, CPU performance started to drop off. Now take the GPU, which doesn't have this particular limitation and is continually increasing performance year by year. So that's GPU and computing in a nutshell. The effects, here's some benchmarks of virtual reactor on a GPU. These plots show 4 different cases. Running single GPU up to 4 GPUs. This is our first multi-GPU release last year, a virtual reactor, anywhere from say 50 or 80 to 400 times faster over CPU on the same machine. Get to more later. Saw recently over 1,000x speed up on the cloud. And what are the benefits here? And this is counterintuitive. So everybody thinks, oh, well, it's faster, so it's faster. Yes, of course. Something that used to take a long time takes less. But flip that around. If it's taking less time, in the same amount of actual time, you can do many more parametrics. And so what this does is it enables much more virtual testing. And I haven't even got to the cloud where you can run many of these cases in parallel due to debottlenecking hardware resources. But with more testing, you can explore more concepts, more crazy ideas, and even enable things like machine learning on the concepts you're testing. But that's not the only thing we're seeing, because as an engineer, I used to run this software every day. I'm not content with speed. I'm not content with more. What I would do, and what I've seen people do for decades, is make bigger models, higher resolution, more complexity, more physical models, more detailed chemical reactions. As we're trying to capture things like, how do you model a piece of trash? What gases come out and what's it doing? And to the point where things that weren't possible even before, ever before, were now made possible. So that's GPU computing. The third enabler we're going to get to is cloud infrastructure. And so with cloud infrastructure, preaching to the choir at this particular conference, virtual unlimited capacity is a major driver for going to the cloud. You're not limited by how many computers you have. Instant access to the latest infrastructure. So as NVIDIA keeps coming out with faster and faster GPUs, our clients are not waiting for their 3 to 5 year hardware upgrade cycles before they can take advantage of it. And these are all demand-based models. So things that we did at the same time to enable virtual reactor in cloud is we moved to cloud licensing to seamlessly transition between on-premise and cloud usage. We just released a metered licensing, which provides virtually unlimited overflow capacity up to the hours on the meter. We are intentionally provider agnostic, so you can work with AWS and Azure and Google Cloud, and you can go through platforms like Rescale to make that easy and seamless. And here's some initial benchmarks. This was published by some early tests last year, done by a third party on Azure, and seeing that on that particular system, we're seeing anywhere from 50 to say 200 times faster performance in the cloud. Now let's put it all together. So let's look at simulation software, GPU computing, and cloud infrastructure. And let's go to my second pretty picture of the plastic waste challenge. This is a global problem. Something like 400 million tons a year are produced annually of plastic waste. And those are big numbers. I get lost in big numbers. I took some of these slides from a great presentation by a brilliant researcher, Kit Windows-Ewell at the University of Birmingham, from our users conference this year. He put it this way: the amount of plastic waste that is produced every year and a half is equivalent to the mass of the entire human population. So this is a lot. Here's the part I really didn't know. 91% of that waste is not actually recycled. I put it in the bin. Where does it go? 91% really ends up as landfill or is incinerated. Of the 9% that is nominally recycled, and you'll see what I mean in just a moment on nominally recycled, most of it makes some sort of low quality second life product. So why not just recycle more? Well, we got a couple issues here. One is contamination. So see this pristine water bottle I'm showing? It's probably not that pristine. Probably had some juice in it. It's sticky. There's junk on the outside. But more than that, it's made out of mixed molecules. So I'm showing one part of it. That bottle is made out of one thing. The cap on the top is made out of a different plastic. The sleeve that goes around it is made out of a third plastic. And you can't just melt these and make a soup of plastics the same way and make a nice pristine water bottle. So I have this idea of recycling. You take the bottle, you go through your recycling, and you make another water bottle. But that's not what happens. You don't have the quality product to do that. These are food grade materials in a lot of cases. No, instead what happens is something called downcycling. Maybe better referred to as downcycling. So you take the plastic bottle, you recycle it, you make something like maybe a carpet. And then you take that carpet, and maybe you can do this a couple times, but eventually it ends up in the landfill. So really downcycling extends that time scale, but really it's just delaying landfill. Is there a better way? What else could be possible to do here? Well, why don't we take this water bottle, and this isn't my concept, we get to who's doing it in a moment. What if you take this bottle, recycle it, and make something like a barrel of oil? Well, wait, isn't that even more dirty than carpet? Yes, but wait, we know what to do with a barrel of oil. We know how to take a barrel of oil, make molecules, and from which that make plastics like the new clean water bottle. And so there's a number of companies. In the last year alone, there's been announcements with what I just showed you. University of Birmingham is working with recycling technologies in the UK. They have a really slick modular process they're developing. I use this schematic from Tech, a company here in the US. And really, they put it well in here. They're saying to take the mixed waste plastics, turn those into the base molecules that the manufacturers purchase to produce the plastics to make the packaging that are widely used today, which when they're trash can be, again, taken back into the base molecule. And you see I'm going around and around. This is called the circular economy of plastics. We have Tech announced just last month their use of virtual reactor for this, their plant that they're building. Encina, I'll get to their story in a moment. They're building a massive plant out in Pennsylvania for processing mixed waste. And take a look at the characteristics of these companies. So remember my traditional use cases, the refineries, the cement producers. These are massive companies, massive infrastructure. These ones I just mentioned, they could be startups. They're smaller, they're younger, they're newer. There's an urgency in their R&D, an urgency to commercialize quickly to address these crises that are at the tip of everyone's tongue right now. There's a flexibility and an agility here to pivot. Does that sound like a great fit for cloud computing? I hope so. So let's take an example. Encina Development Group, who presented at our conference, then took a large model they had, provided to the team over at Azure, who did a test on some of their larger systems. And here's some of the benchmarks. Now again, details don't matter, you can look it up. What we see here is the CPU serial, the blue on the very left was running 0.04 seconds a day. What does that mean? It means nobody was going to do that model ever before. It just takes too long. It'd be quicker to build the plant sometimes and see what happens and try and simulate some of these things. Started looking at it on systems that had V100s and A100s, which are different generations of GPUs. Looked at speed up the fastest there on the right, and that particular study had 4 A100s on it, running 500 times faster. Now we have something totally meaningful, totally practical to do. And here's the cool thing with that study. Yes, the system with A100s is more expensive per hour to run in the cloud. It's the latest and greatest. Guess what? It was the lowest cost simulation they ran because it finished so quickly. So the cloud computing is enabling these agile companies to not just quickly bring their technologies to market, but do it in a highly cost-effective manner. And I have other benchmarks. They've not even been published yet. They'll be coming out soon through our Azure team. There's the ability to right-size instances where you might not need 8 GPUs on a system. You might need only 2 or 3, and there's ways to get that. We've also seen benchmarks of over 1000x, and stay tuned for that in the near future. This type of work's getting international recognition. Our work with TRI was highly commended at the 2020 iChemie Global Awards for process automation and digitalization. And then now this recent work with Encina. This year, we were just last month at the Hydrocarbon Processing Awards. We're a finalist in sustainability category. And next month, in fact, next week is the iChemie Global Awards over in the UK. And our work is a finalist in both the sustainability and the process automation and digitalization categories. So cheer for us there. Let me close with this. There's an urgency. The rate of innovation is critical. I showed this chart earlier for the work with TRI, and we saw the 68 times speed up between 2009 and 2019. That's a long period of time. Now, TRI was building other technologies at that time, so it's not just that they're working on this one case. But we asked the question, what would happen if the latest GPU technology and the latest cloud infrastructure were available today on these types of problems? Now, I had to change the scale. Take a look at this. Here is that in the middle is that 68 times speed up we saw in 2019. Today in 2022, we're seeing over 1,500 times faster running GPU computing on the cloud. Totally game changing. So what does the future hold? Look, simulation software, GPU computing, cloud infrastructure are coming together to address some of our planet's toughest sustainability challenges. And so what does the future hold? I'm not really the one to tell you that. I work for the simulation technology company. We're going to keep adapting and meeting our customer needs. And we are really privileged to work with companies like NVIDIA, who both GPU hardware and software are enabling this. We work with a lot of the major cloud providers, AWS, very closely with Azure. We're working very closely with Rescale to get the platform out there as a platform to get cloud usage easily out there for everybody. But where the future holds is going to be people that are listening to this talk that have an idea. They have a crazy idea that might seem impossible. And using these technologies, they have the power to take this impossible idea and make it a reality. So here's to you. Thank you for listening. Thank you for joining us at Big Compute. My name is Peter Blaser with CPFD Software. Look me up and ask me any questions. A couple of simple next steps. Feel free to try Barracuda Virtual Reactor at one of our monthly web-based training classes. And you can learn more at cpfd-software.com. Thank you so much for your attention. Have a great rest of your day.